Hello, welcome back again. And now that we know how to operate with algebraic vectors in 2 and 3D, we're going to take a look at some examples. So in the next example, we have to find a point on the x-axis that is equidistant from points A and B as described. So I'm going to start off with the point on the x-axis. So we have to define the point on the x-axis. Obviously, notice here we are in 3D. And I'm going to call this point on the x-axis the point P. Remember that on the x-axis, the y and the z coordinates will be 0. So it makes sense to identify this point as some point with coordinates x, 0, 0. Now we want the point to be equidistant from A, which is 3, 1, and -2, and from B, which is 7, 0, and 3. So the distance from point P to point A, and I'm going to write this down here, from P to A, we'll have the distance, which we will find out, defined by the coordinates x minus 3, 0 minus 1, 0 minus -2. So all we're doing in here is the difference between x, between y, and then between the z coordinates. So in other words, we're going to say that this would be x minus 3, -1, and +2. Now, the distance itself will be described or found by using the formula square root of the x component squared, x minus 3 squared, and then y component, which is -1 squared, and z component, which is 2 squared. So in the meantime, we want this same point P to be equidistant from B. So here we're going to write from point P to B, we want to find the distance, which is defined by the coordinates x minus 7, 0 minus 0, and 0 minus 3. Again, in a similar way, we went x minus 7, 0 minus 0, 0 minus 3. So this would be x minus 7, and then 0, and then -3. So this distance in particular would be equal to square root of x minus 7 squared plus 0 squared plus -3 squared. So we want these two distances, so the distance of P from A and the distance of P from B, to be equal. In other words, we want this length equal to this length. So what we're going to do is simplify inside, and we'll have for the blue one x minus 3 squared, which I am going to write in expanded form, x squared minus 6x plus 9, plus -1 squared is plus 1, and 2 squared is 4. So this would be equal to x minus 7 squared, which is x squared, minus 14x plus 49, plus 0 squared is 0, and then plus 9. So notice that we have x squared in both sides, so that simplifies to no x squared. -6x, -6x plus positive 14x, that will give 8x. And then I will take all the numbers to the other side. So here we have 9 plus 1 plus 4, that's a 14 that is going to the other side as a negative. And we also have 49 and 9 waiting here, which add up to 58. So we have 8x equals -14 plus 58, that's 44. 8 minus 8, yep. And x must be 44 over 8. Or in a simpler form, divide both by 4, we have 11 over 2. So therefore, we're going to say the point P must be 11 over 2, 0, and 0. Now, in the next example, we're given vectors OA and OB. As you can see here, we are in 2D, and I purposely mixed up the questions with 2 and 3D just to increase our vigilance in analyzing and looking at the information critically. Illustrate each of the following vectors on the graph and write them in standard form and find the sum of the vectors. So let's get started. Now, vector OA is given in component form, right? So both vectors, you're given the coordinates. So these are the component form or coordinate form. So if we want to write them in standard form, means that we have to describe them as vectors, or kind of vector form. So that must be 1i plus 2j. Vector OB, on the other hand, is 3i plus negative 4j, which is minus 4j. Don't forget the vector symbol on top. Now we have to use the standard form of the vector to determine a plus b. So in other words, a plus b would be OA plus OB. Or we'll say that is I plus 2j, right? OA is I plus 2j, 1i plus 2j, and OB is 3i minus 4j. Now, it makes it easier for us to operate with vectors when they are expressed in terms of their components, because when vectors are going in the same direction, so if they're both j vectors or I vectors, I'm going to make this I because it does look more like it. So if we want to add vectors in the same direction, we just work with their magnitudes. So we're going to say this would be I plus 3i, or 4i, and 2j minus 4j is minus 2j. And that would be vector A plus B. Now, in the same way, we're going to do A minus B. So again, I plus 2j minus 3i minus 4j. So this would be 1 plus 2j minus 3i plus 4j. Or negative 2i plus 6j. And vectors, vectors everywhere. And now we're going to use a Cartesian plane to draw the vectors from B. So 4i minus 2j means that the component form of it will be 4 and negative 2. So position at 0, 0, and then 1, 2, 3, 4, and negative 2. So this is where the head of the vector would be. And voila, we got the vector OA. Now, in the same way, we're going to draw the vector negative 2i plus 6j, which is basically negative 2 and positive 6. So 1, 2, and then 1, 2, 3, 4, 5, 6. We went a little bit far. That's because we're ambitious. Here we go. And this would be your vector OB. Now, operations with algebraic vectors, as you see here, as we saw this together through the numerical examples, can be summarized this way. So it's a summary. You can take your time to read through, actually. And if you are simply watching the video and you don't have a handout with you, just stop the video and you can take notes if you wish. The idea is that if we have vectors in 2D, described by their components, then when you add them, we simply add or operate with the components. Same with 3D, but you have an extra coordinate. So now when you multiply a vector by a scalar, k, it means that this scalar will multiply each coordinate, so kx and ky. In 3D, same idea happens, but we have a third coordinate. So let's take a look at some examples. We have vector A, 2i minus j, vector B, I plus 2j. So what kind of vectors are they? Are they 2 or 3D vectors? So that's a question we should always ask to ourselves when we are working with vectors, right? So A plus B would be equal to So I'm going to start with 2i minus j plus 1i plus 2j. We add the i's to the i's and the j's to the j's. So we have 2i plus I minus j plus 2j. And simply operate with coefficients here. We have 3i and then plus 1j. If we want to find the magnitude of a plus b, no problem. So we're going to go ahead and square root the square of each coordinate. So 3i squared plus j squared. So that would equal 9 plus 1. That's a square root of 10. So we can use the component form of a plus b, which is 3 and 1, and then substitute into the magnitude formula. And here is an example for you to try. This time we chose 3D vectors, but the idea is the same. And we have 3 vectors. So we have vector A, B, and C, vectors A, B, and C, and we want to find A plus B minus C, which means that we have 2i minus j plus k. That would be vector A, plus vector B, which is I plus 2j plus k, plus vector vector C, which is I minus 2j plus 3k. So here we go, we're simplifying now. We have 2i and 1i, and then minus I equals 2i. And then we have negative j plus 2j, and then here we have minus negative 2j, which is a positive 2j. So that equals 3j. And last we have 1k, another k, and then minus 3k. So 2k minus 3k is minus 1k. So obviously we want to use the vector symbol everywhere. We have to add that on top. Don't forget that, especially on a test. And there we go. We have the sum. The expression a plus b minus c expressed here in standard form. Now we have to find the magnitude. So for the magnitude, we're going to use the component form. So the component form of that same vector would be 2, 3, and negative 1. So we'll have the magnitude of a plus b minus c equal to the square root of, 2 squared plus 3 squared plus negative 1 squared. So that would be 10, 14, root of 14. In the next example, we have the multiplication of a vector with a scalar. So these are kind of easy and fun examples. So we have vectors A, 2i minus j, and B, I plus 2j. They're in 2D. And we have to find 3a plus 2b. So that means 3, 2i minus j, plus 2i plus 2j. So in this case, we're multiplying vectors by a scalar, which means that we have to bring each coefficient in. So this would be 6i minus 3j. And this would be 2i plus 4j. So 6i plus 2i is 8i, and then plus 1j. And again, don't forget the vector symbol everywhere. I like to leave this for last because I do recognize it's a little bit tedious, but it's necessary. So now that we have the standard form, we can write the component form, which is 8 and 1. And the magnitude will be equal to the square root of 8 squared plus 1 squared. So that's a square root of 65. Now your turn to try. This time we have 3D. So we have A and B and C here. So we have to find 2a plus 3b minus half c. So here we go again. We have 2i minus j plus k plus 3i plus 2j plus k, and then minus half of 1 minus 2j plus 3k. So again, this would be 4i minus 2j plus 2k plus 3i plus 6j plus 3k minus half I plus 1j minus 3 over 2k. Again, continue simplifying, so I'm going to bring together all the i's and then the j's and the k's. So here go the i's. So we have 4 plus 3 is 7 minus half 6.5, which is 13 over 2. So 13 over 2i. And then we have the j's. So for j's, we have negative 2j plus 6j plus 1j, so 7 minus 2, that's 5j's. And 2k plus 3k minus 3 over 2k, that would equal 2 plus 3, 5, minus 1.5, 3.5, which is 7 over 2k. So again, don't forget the vector symbol everywhere, and this is going to be quite some work now. And don't forget to write the vector in component form before you start finding the magnitude, which makes it easier. It's not a mess though. And we're going to say that the component form of this vector would be 13 over 2, 5, and 7 over 2. So the magnitude equals the square root of 13 over 2 squared plus 5 squared plus 7 over 2 squared, which will make it 169 over 4 plus 25, which I'm going to express it as over 4, so 100 over 4, which will make it easier. And 7 over 2 squared is 49 over 4. Square root it. So that would equal 179. And plus 49 is going to be 180 plus 50, 230, 228 over 4. Okay, and let's see, we can simplify this to 5, 7. So that would be the square root of 57. In the next example, again, we are given vectors, this time in component form, and we have to find the sum a plus b and 2a minus 3b. So similar to what we were doing with the standard form of the two vectors. I think you can try this on your own. And I'm going to move on to the next question, which sounds a bit more interesting. So we're given some vector c with coordinates t and 12. We're missing one coordinate. We're told that vector c is parallel to vector a. And vector a is right here, 4 and negative 3. And we want to find the value of t. Now, if two vectors are parallel, it means that they can be expressed as scalar multiples of each other. Okay, so therefore we're going to say that t and 12 and 4 and negative 3 must be related to each other or connected by some coefficient here, k. So what that means is that we can say that t must be 4 times k. Let me just write one more step in here, actually, just to make it more clear. So that would be like 4k and negative 3k. So that means that t equals 4k and 12 equals negative 3k. So the multiple actually, or the scalar that we have in this case would be -4. So you just divide by -3 here. So when you go back now to t, then we're going to say t must be 4 times -4. So that will make t equal to -16. So we'll say that t equals -16.